All right, so again, we're going to continue. We are at the heart of the GPT. This is the second lecture of this, the second video. As I was saying, our approach is to use object-oriented classes for everything, because otherwise it'd just be like this, right? Block, and then I can just instantiate 6 blocks. But when we look at block, we will see that it's actually quite a bit of code that's going on in there. But this is such a nice solution because it makes it a lot easier. So if you notice here, it's got an embedding, and an embedding for the semantic embedding from 512 to 64. It's got the positional, from vocab size to 512, right? So that's what the embedding is. And then positional embedding for the position to 512. Then we did this, which was and then sequential, which we will see this again later in the semester several times. There's 2 ways in which I will code. And then in sequential, I gave you the example previously. And then after that, a few layers. So now in forward is where we bring everything together. Okay, so forward is exactly where we bring everything together. And this is kind of what the baby GPT was, if you remember. So if you notice here, IDX is going to be the data that comes in. So that's going to be our text. So think of it as X. And then targets is going to be our Y, right? So in this case, what does that mean? It means simply that a sentence comes in, the cat is sleeping, and then if for IDX, and then for targets, it's the same sentence but shifted by 1, right? What we just did in the previous one. So it's the 2 sentences, okay? Notice here in this step, I'm just taking these variables B and T. So I want to know what the batch is and the sequence is as well, okay? And then notice, just like in the baby GPT, IDX would go into token embedding to create the tensor, right, of size, batch size by 40 by 512. Do you guys see that? And then notice over here that positional embedding, just like we discussed before, would take in an input and produce also a tensor. What is the size of that tensor? The same as the size of the embedding. So n by 40 by 512. Now, if you remember, what is this? We talked about this, and I did an example in the previous video of torch A range. Remember that I gave you this thing when I was first learning the GPT. I was confused by this because I thought, but X has to go in, right? But it's not X that goes in. Instead, we just have a list of all the positions from 1 to 40, for instance. So 1, 2, 3, and each one of those gets a vector of size 512. So we've talked about that. All right. So once we have these 2 embeddings, you remember that all we do is we add them, right? Same thing as before. We just add them together. Now, in our previous example, baby GPT, this section here. Oh, I'm sorry. I'm in the wrong place. So I'm here. So here, this is where I was. So in the previous section, these 2 statements here were the attention layer. Do you guys remember? We would do the K, Q, V, and all that. That's still happening, but it's happening in blocks. But if you're in each block, but remember that each block this object blocks is essentially the 6 blocks that we instantiate. Okay, so we can create a block and then another block and another block. And by using an n sequential, we're guaranteed that the input is going to go through all of them. It's just like the way that PyTorch works. If we had to do it the other way around, it would be a lot more code to write. All right. So then essentially just think of this. We have to drill down into blocks, of course, but just think of it as that's where the attention mechanisms are for the input. And there's going to be many, many attentions that it's going to go through. Okay. So think about it. Each block has 8 attention heads. And then, so there's 8. then another 8, then another 8, then another 8, 6 of them. And every time the input just gets transformed and comes out, goes to the next one, and so on. Right? So that's the idea. And then this LNF is a normalization layer. So just think of it as, dividing by a specific number, something, some kind of a normalization approach. So we can skip that for now because it's just a normalization. And then finally, once we are here, we run the final X. So notice X goes into blocks, then it goes through the normalization. And then finally, X goes into LMFFW head to produce something called the logits, which we have talked a little bit about that term. But notice that this LMFFW head is really what? This embedding, an embedding to vocab size. Do you see that? So that last part of the baby GPT. So essentially, all of this part, we can come back to later, but this is essentially the optimization. So I will come back to this in a little bit, but I really need to focus on blocks, all right, for now. Okay, so if I run this right now, it'll give me an error because I haven't defined blocks. So that's the next step that I need to do. I need to figure out how blocks works. So I'm going to go into, here it is, block, right? Because blocks is really just this variable that has a list of 8 blocks, the 8 heads that need to run in parallel, okay? So now think of it this way. So far, we've defined, we are at the point where we do like, we are at the point where we created the embedding and the positional embedding, right? And these, we add them, and that gives us a block, which is n by 40 by 512. Do you agree? That's where we are. Then we go into that NN sequential. But that NN sequential, so let's imagine we're here. That's the tensor. N by 40 by 512. By using that NN sequential, we have 6 blocks. And so this tensor will go in and it'll go into 8 attention heads in parallel. Remember, we talked about that, right? Then they get concatenated. There's a feed forward layer here. And what comes out of here is N by 40 by 512. Why is that nice? Because then that input is just like this input, so it can go back into the block again. But it's been transformed, right? So here it's been modified. So now it goes in here. And guess what? How many attentions do we have here? We have 8. Dot, dot, dot. There's a feed forward. And guess what? What comes out of here? N by 40 by 512. Do you see that? And that keeps happening until we get to the very last one. And guess what comes out of that? N by 40 by 512. The 6 blocks. Once I'm done with the 6 blocks, then I have a feed forward layer, to convert this for the vocabulary, etc. But that's essentially the idea, okay? So the data is flowing like that, and we have these 8 heads. All right, so yeah, so that's what we're seeing, right? So what creates the 6 blocks, and the 8 heads are going to be in block. So here we have, so here we have So then we have X that goes into the 6 blocks, and each block will have its own head and so on. So now I think we are ready, hopefully, to look at each block. And that's going to be this one over here. See another little handy class. Okay. And notice the same approach. I create a class, called it block. It inherits NN module. And it's got two nice little functions, init and forward. Do you see that? This is always going to be the case. Init contains the super init to instantiate the inherited class. This is usually where we provide the parameters in the init function in the constructor. These are like the parameters that establish things. So for instance, n head is what number? 8, because there's 8 heads, and n embedding is 512. So this is the other parameter. All right, here we do this is what I said. Remember, if you're going to have 8 heads, it needs to come back to 512. So you want to divide here. So, you divide 512 by 8, and that gives you 64. So that's the new dimension, the head size. This one here is the multi-head attention. So every block, as I said, has 8 heads to pay attention. That's like the whole trick that we've been discussing, and that is accomplished by this object here. So we also need to define multi-head attention. So multi-head is just a class made up of heads, where heads is going to be the attention, that whole attention mechanism. All right, so we do multi-head. We provide n head, which is this one, 64, or actually it's 8, and head size is 64. So we create this object SA, okay, for the multi-head attention, and then that's going to be followed by a feed forward, which is just a regular neural network mapping 2048 to 512, or 512 to 2048, 2048 back to 512. So notice all we do in the init is we instantiate these, and then in the forward is where we put it together. So if you notice here, I don't use the NN sequential approach, and instead I use the approach where something goes in through the thing, comes out here, and then this X is used in the next one, and so on. All right, so notice here that we take X, we run it through these normalization layers, which again, just think of it as like putting things in a specific scale from -1 to +1, etc. This X goes into SA. SA is the multi-head, right? And then it'll do all the 8 heads, concatenate them, all of that. Once that's done, you have one single tensor, n by 40 by 512, that comes out here. And notice that that gets added with the original input. I had talked about this before. What are these things called? They're called residuals, okay? So let's talk about it a little bit, because they're prominent in all of neural networks. All right, so I have here n by 40 by 512. So let's think about where residuals come from. So a residual, right? What was it? So there used to be a problem called the vanishing gradients problem, okay? And that was a problem that plagued neural networks for a very long time. So they created deep learning, and they're like, oh, let's just add more layers. We add more layers, we can solve any problem. But what is happening in a matrix multiplication, if you notice, is that you're consistently multiplying numbers that become smaller and smaller. So for instance, imagine that the weights here are like 0.5 times 0.5, right? Then you can expect this value later on is going to be 0.25 times 0.25. And eventually, as this network gets really deep, what's going to happen? These become like 0.005 times 0.00005. So at some point, they're essentially going to become what? 0. And then what happens? Let's say that you still have a few layers to go. Well, at this point, you have a useless neural network. Do you see that? And so for the longest time, it seemed like the solution of deep networks wasn't going to work. But then they invented this idea of residual, which is like the most simple thing. So as you guys know, going from one layer to another simply just means that X goes into a function to produce Y, right? So essentially in that direction. So X goes into the matrix multiplication and it produces this Y, the next layer, right? Essentially. So the problem was that things were going in like this, and this was happening, the vanishing gradients. So one of the solutions was, well, what if we just passed X directly to Y, there wouldn't be a vanishing gradients, right? You agree, but that wouldn't solve anything. So what if we combine them? Let's pass X, but also X as it goes through the function. So here's a little bit of learning plus the original data, and that is passed to the next level. It doesn't have to happen in every part of the neural network. As you can see in the LLM, it's not happening everywhere, right? But it is happening in a few strategic places, such as here. So, it goes into a multi-head. What's a multi-head? It's essentially a block, right? So it goes into a multi-head, and the X goes in, and then you add it with itself to become a new X. Do you see that, guys? That's a residual. So it's applied there. And then this X is used in the next step. So you normalize it, then it goes through the feed forward, but you also pass it through a residual. And that provides a lot of help in the depth of the neural network. Okay, and not diluting that signal, if you will. It's like it's being diluted, but then you like provide the information again. And that alone helps the neural network a lot. This is not just used in LLMs, it's used for image. All those image models that you've heard about, they also use it. Anything where it gets really deep, it's essential. There's, in fact, for image processing, the most famous neural net is called the ResNet, residual network. Okay? So the idea is super simple, but like I said, we've seen this concept of adding things several times before. As long as the dimensions are correct, it's going to work out. But because we're always doing what? N by 40 by 512, we have no problem. Do you guys see how that little concept is so useful? That consistency allows you to do a lot of things. And then the weights just have to be adjusted to work. Okay? All right, so I did this part. That's the block, which goes into a multi-head attention. So now we have to go into that one, right? So let's trace the tensor. So the tensor goes into a multi-head. So that's going to be this one over here. Okay. And this is going to be the trick here is there's a trick similar to the before, a little bit of a coding trick, but it's what gives you the heads. So notice over here, you're going to be using something in PyTorch. Notice again, so I should state, what am I doing? I'm creating a class called multi-head. It inherits NN module, right? There's two functions, init and forward, right? Init and forward. And in init, we instantiate several things. One of them being this modular or module list, NN module list. So that's a construct in PyTorch that allows you to create a list of tensors. That's essentially what this is. If you notice, for index in range num heads. How many heads? 8. So this essentially creates a list. Let me go to the whiteboard. This essentially creates a list of heads. So it's like head, head, dot, 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 head. And there's 8 of them. So 0, 1, all the way to 7, right? And later, once we finish, we'll be able to concatenate them to create a tensor. So remember, they're n by 40 by 64, right? So when we concatenate them, they'll become n by 40 by 512, which is the concept that we had talked about before. All right, so we can go back and take a look at that. All right, so I have module list of 8 heads initiated. Notice this is just an NN linear, just a neural net mapping from 512 to 512, right? So you can see it's just another layer that I'm adding. This could be 512 to 2048, but in this case, it's just 512. So now that I've instantiated these elements, I just define the architecture. So notice over here, heads is instantiated here, and then I can just use it. So notice how clever this is. So you do for H in heads, right? There's 8 of them. You instantiate it, but also at the same time, plug in the X. Do you see that? So that the X comes in, right? So think of it like this. So this is another like tricky part of the code. It's a list of 8 heads, right? So you have, H, H, dot, 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 H. So essentially in the neural network, X comes in and it goes into, so it comes in like this, and it'll go into every single one. H, oops, H, X. So essentially, you just shoot the X into this. This has the attention and everything. And what comes out, this is what should be N by 40 by 64. And what comes out of here is N by 40 by 64. But you do it 8 times for the 8 individual heads. So this X also goes in here. Remember that we do this in parallel. They're independent of each other. Dot, dot, dot. Dot, dot, dot. And then all these 8 heads are just going to be concatenated together as a previous example that we looked at. You guys see that? So that's essentially what's happening there. So if we look now, so essentially, in forward, right? X comes in, it gets added here, but there's 8 of them. And it can be the same operation because it's the same X. And then once they're done, the output comes out into this list. Guess what? We just concatenate it on the last index. That's what this dim -1 is. It just means concatenate on the last index, and boom. What do we have here in out? What's the dimension? N by 40 by 512. And we have gone through all the 8 heads. Okay? Once that's done, out just gets projected one more time from 512 to 512. So that's another layer. So you can think of it as that n by 40 by 512 is there. In the neural network, you can think of it as this is 512, and I just added another layer, and now it's 512 again. So essentially, it just becomes n by 40 by 512. Remember that there's a set of weights here making all these connections that needs to be learned. And that's the trick. You give it a little bit of room to have one of these layers of connections that must be learned. Okay? So remember, you're just, predicting going forward. Okay? And we're almost done, right? So at this point, we have, and like I said, these dropouts we'll see later on. These are just simple things that modify the values in the tensor. But we have the multi-head attention, which came from, so we were in the blocks. The blocks have 8 heads. It does the whole thing. And the final part is, well, you might ask yourself, so what is head? It's very nice to think of head independently because X goes in and something comes out, right? So that's essentially what we have, n by 40 by 64 goes in, n by 40 by 64 comes out. Boom. So you can treat this totally independently. So now I'm going to add here my last one, and there's this feed forward. So, but this one is so straightforward. We'll see it though. It should be, where is this feed forward used? I think it's used down here. But that's a very simple one. We'll take a look. But finally, we're here, head. And this is what we spent the last 2 weeks talking about, the attention mechanism, but this is where we bring it together. Okay. And there it is. So remember, take the same approach. We define a head class. Then I have an init and I have a forward. And that's it in my class. This, as you probably can see, is the attention scores and the trill with the mask and everything we've discussed before, right? So you can see here, we defined the head size, which is 64. You guys remember that when I did the examples, right? I said that I was defining W bias, and then I would do the actual matrix multiplication, and that was several lines of code. But then I showed you that all of that gets done with NN linear, right? So you remember that NN linear, and I can do a reminder here. So NN linear is the basic building block of neural nets, right? So what was this? If you remember, we always would define an X, then a W, then a bias, then we would take X, matrix multiplication, W plus B, and that would give us, that would give us Y. Right? You guys remember I did this in the attention with Q and K, but there's a shortcut, which is much better, which is to define just NN linear. And then inside NN linear will have its own. So think of it as I'm defining here my N, I'm going to call it NN1, right? As an NN linear, okay? So then NN1 automatically, guess what? Has a W. Automatically. And guess what? Has a V. Automatically. Do you guys see that? And so that's the beauty of it. And also, the way it works is like this. X. y. So essentially it implies that inside it'll take that x times that w plus that b to produce the y. Do you guys see that? So that's essentially what's happening behind the scenes, but this just abstracts a lot of that to make our lives very convenient. And then what we define here is the dimensions of the neural net, which we were doing explicitly, and this had to match this and that and so on, if you remember. So that was much more complicated, whereas here it becomes a lot easier. All right, so let's go back to just, I think once we finish this, we'll be able to run and train it for a little bit, and then we'll talk about that. So here I define the head section. So I'm going to have KQV. We spent a lot of time talking about KQV. They were all NN linear, right? No, I'm not using a bias here, but you could use a bias. We have N embedding, which is head size is 64, right? So this was 512. So we're mapping from 512 to 64. Okay. The trill, guys, we already talked about the trill, right? We did this last week. We talked about the mask and how that works. So we define all these operations. So now the logic is exactly the one we had before. X comes in, which is actually n by 40 by 512. It goes into key and query and, oh, I'm sorry. All right. So X comes in, right? Goes into key and query, right? So you remember we convert X into KQV. Exactly the same thing is happening here. But remember, we compress it to 64 so that we can have 8 heads that can be concatenated. Then if you notice, this is the same thing. Now we take that K and Q, matrix multiply them. We had talked about the transpose already, and there is this normalization, dividing or multiplying. This is actually like dividing by square root of something. But here's a multiplication times 64 to the minus 5. So it's like a constant. Sorry. Okay. All right. And so you can disregard that if you'd like. And just remember, this is KQ. Okay. What did that produce? The attention scores. If you remember, here it's being called way. And then once that attention scores, we've already talked about all this. The mask is applied, the trill, right? That was the whole discussion of last week. Why did we assign minus infinity? Do you guys remember that? We talked about it last week. So that could be a question on the exam, right? You know, why did we do that? Why was that necessary? Go ahead. The softmax, right? Because the softmax is going to be applied later, and the softmax is going to create a probability distribution that adds up to 1. So if the minus infinity is not there, we can't do that. You see, that's an exam type question for that, guys. All right. Once that's done, way, then it goes into softmax, and that's it. This, again, a dropout, don't worry about that. Assume the values are just getting divided by something, all the values for now. Then what did we do with the attention scores? First of all, I should ask you, so what is the dimension of way right now? Batch size, comma, 40 by 40, correct? Remember, it creates that square matrix, 40 by 40. And then what happens to it? We do V, and we matrix multiply way with V, correct? And that gives us what? N by 40 by 64. Perfect. Do you see that? If you guys, the trick to understanding this is to understanding those tensors, as I said. What is the shape of the tensor now? What is the shape of the tensor now? And so that gives you a sense of the operations that have happened. That's it. We're done. So that was the attention head, right? And so now the X has gone through one head, it'll go through 8 heads because of this part here. And then they will be concatenated. All right, so I think if this is correct, all of it has been defined now. If I haven't defined one thing, the feed forward, right? This one, I need to add it. This will be needed by, yeah, block needs it. Right? But we should be able to train on Huck Finn now, hopefully. Okay? So let's see. A feed forward, again, create a class. Notice it's got def for init and def for forward. 2 functions. Always, guys. Always. Init, we instantiate the inherited class. And then notice I'm once again using that NN sequential. Do you see how this is a perfect example, right? Usually, I have an X that goes into something, comes out, that becomes the input to the next one, comes out. Notice here, that's not happening. There's no X here going in. There's just net. So X goes into net, which is this one here, but it is assumed that it'll go through all of these, okay, in sequence. So 512 to 4 times 512, and then 4 times 512 back to 512. Remember, we had also talked about this. And here you have these ReLU activations as well. Remember, again, just takes the values, and ReLU just doesn't pass any negative. So those negative values become 0, and positive values are passed. So think of them as like filters, if you will. Got it? All right. So I think we've got the architecture. Now let's proceed, cross our fingers, because we're going to train Huck Finn, right? Unless I've missed something. So I have all these defined, and I'm going to instantiate these, and I want to get this, and then we'll talk about that part. And the amazing thing is, regardless of how complicated a GPT might seem, the optimization function is exactly the same, even if you're training Iris or anything else. So let's go over here. I think I had modified this, so I want to make sure. All right. So now let's see. The last thing we did, oh, the whole thing actually like died on me. All right, well, let's change the runtime to GPU since it might train faster with a GPU, right? It is, after all, a whole bunch of layers. So let's do that. So hopefully that's set now. So let's go ahead and start. Invoke Torch. I think like it crashed on me or something because it's mounting the drive also. Huh. No, the drive's there. Okay. Okay, so there it is. So that worked. Then this part, the parameters, load the Huck Finn. Okay, got some data. There's the vocabulary. There it is. 88 characters. The dictionaries. The encode part. The decode part. This is, remember, this you can get rid of if you want, because I was only doing it to demo how it works. Get batch, you definitely need. This is the key for training. It's randomly grabbing the data from Huck Finn and training on it. Okay. All right, here we have class head, no errors, so that's good. So that means everything is good. Forward also. Multi-head attention, block, and now the GPT model itself. Did it, what happened? Yeah, there it is, right? So green check. Okay, so now everything is defined, and the next step should be to instantiate everything. So we instantiate the GPT model itself as model. We assign, notice here, model to the device GPU. That becomes M. That's how we're going to reference it. And then we need to instantiate a new thing, if you've never seen this, called the optimizer. So we'll learn this. Don't worry about this. We'll learn about this dynamic in the second half of the semester, right? The optimizer, but this is the thing that trains the weights, okay? The way that it works is there's essentially, this is the stochastic gradient descent algorithm is in there. So in TensorFlow, you do everything with the architecture, but you do very little in terms of like the weights, the gradients, that whole algorithm of backpropagation, the derivatives, everything that's going to go with that is done behind the scenes. So that this algorithm does the heavy lifting. Notice that we provide a parameter called the learning rate, which is the parameter that decides how big the update will be to the weights. And notice that the way that we link the optimizer to the model is by providing this m dot parameters. So that m dot parameters is every parameter in this GPT, all the weights, all the biases that for the last 2 weeks, I've been creating all these weights that were always random. They had the right shape, but they were random, right? Remember all of those? That's what this is. But now these weights need to be updated, okay? So I'm going to go ahead and do that. Let's see if it works. Okay, perfect. So it instantiated the GPT. I have my optimizer. All right. And now let's see if we can get some activity going on. This is the whole training loop that every time we train something, we're going to use this approach. Okay. So let me just run it to make sure that it actually works. Right. And then estimate losses not defined. Yes, I know where that function is. This one, estimate loss. This is the moment of truth, right? So this is actually where the model would start getting data, training the weights, and then once it finishes, we can ask it questions. I mean, it's not going to be great, but oh, I think it's running, right? So step 0. Yeah. Okay, step 0. There you go. All right. So it is running. So now that's great. So I've shown you can take some data, right? You take this code, you understand the basics of how the architecture works, all the layers, all the blocks, etc., the transformations, and then you understand that we start training this code. Okay, so let's take a look at what this is doing. Let me just see. And notice that, do you see that I'm using a GPU and it's taking a bit, right? So this is what I was saying about why. Because there's 6 blocks and there's 8 heads. It starts to add up. So I would be very happy if I saw step 1. Or step, I guess it's printing every 500 or so. That's the interval. So I assume it's working correctly. Okay, so now there it is. Perfect. Let's take a look at this function, okay, or this for loop and see what's going on. Remember, all I've done is I created this thing called the optimizer, right? And now I'm gonna go through this code here. Let's switch to the whiteboard while it's doing that. Okay. So that's the training. Okay, so here we are. So I created the model, by instantiating that GPT class called GPT model. That's the whole architecture, right? That takes in the data and produces a tensor. If you guys remember, what is the input to this model? Is it n by 40 by 512? This could be an exam question, or n by 40. What is the input to model? N by 40. Very good. Because the nn dot embedding takes care of that, and that's inside the GPT. Very good. Perfect. So now we've got also this thing called the optimizer. And this is always going to be torch, optim. It could be atom, or another one is stochastic gradient descent, SGD. There's several variants of these things, but in reality, they're all like the same algorithm. So it's not like they're different. All right. So in this case, this one is going to be atom, which is supposed to be like stochastic gradient descent, but like more efficient. Okay. What's really important for you guys to note is that they're connected, right? So one of the parameters that goes into this is the parameters of the model. So this model over here is linked here. You do model.parameters, like that, okay? You link it, and then also the learning rate, which is going to be a thing we'll talk about all the time. Learning rate. So I think I'm using 0.03 or something. This is we'll do an exercise in the next 5 weeks of the semester about this. Okay? For the intuition. But for now, this is how it works. It always works like this. All right, now comes the idea of training. We train in batches, right? So we train in batches. So I'm going to do here. So there's always like two for loops, if you will. There's going to be like the number of epochs and then the number of batches, for instance, right? Or some notion of that. In this example, we just need one because get batch takes care of that for us. So if you notice, we're going to do for I or iter in range max iterations. Max iterations. This is really important because in this, the way this code is written and the way that that function get batch is written, get batch every time just gets a random batch of 32 sentences, right? Or 64 sentences from Huckleberry Finn. But the more books you have, right, the more times you need to go in there to extract a batch. Do you see what I'm saying? So you grab a batch, then you grab another batch, then another batch. But if I have more books, now I have to grab batches from over there, from over there. So this value, the higher it is, the more likely you are to get batches. Do you see that? But the longer it's going to take to train. So this is one of the complicated things. That's why it's nice to have 1,000 GPUs or 100,000 GPUs because of the way that it works. Okay. All right. So we're going to essentially, we're going to repeat this problem up to maximum number of iterations. This is determined by your resources, GPU power, amount of text data that you have, also how good your model is or comes out to be. So the next thing is, I'm skipping some parts from the code because they're really not super relevant for this part. Like those first 3 lines just have to do with like printing the law, so we can ignore them. So really what matters is we grab the first batch. We grab the first batch, XB, comma, YB, using the function get batch. And, you know, it uses this term train because we're using the train part. Got it? All right. So now, what do I do with that X? What is, first of all, what is XB and YB? What is XB and YB? We already saw it, right? So XB and YB XB and YB was this. This is XB. This is YB. So if you remember, in this example, I had 4 sentences and the length is, what is it, 40 or 16, I think, 16 IDs. And they're already shifted. Remember that they're already shifted. So the top one, 145.61, notice 45.61. And then 82.65.65, 82.65.65, 1. So get batch takes care of that. Finds a place in the book randomly and extracts X and Y. So it's the same sentence. It's a sentence and the same sentence over here, just shifted by 1 so we can predict the next term. All right, perfect. So then let's go back to the whiteboard. So I grab my XB and YB, and what do? I simply invoke model, this guy over here, right? Model. What does model do? Model takes XB as input. Why? Because it's an n, 40 tensor. It'll, once it goes into model, it'll become in there because of the NN embedding N40 by 512, right? Okay. And what should come out at least is what, you know, the term could be logits, for instance, or it could be YB hat, but that's really hard to write down. So let's go with logits. But you can see what it is like the sentence, right? XB and YB are the sentence and the same sentence shifted. We want to get that last word. So the model is going to try to predict YB. Given XB, it's going to try to predict YB. Do you see that? Okay, so let's call it logits. All right. And then we would have a function loss, which is going to be a cross entropy. We need to talk about this later, but for now, let's just assume that's the function that we use. And essentially, what this allows you to do is to compare two things: the predicted values, logits, with with the YB. Very good. So I'm going to do logits with the YB. Exactly. Because the YB has the sentence that I want. I'm giving it the cat is, and it's telling me cat is sleeping, and I want that sleeping. So I want to learn how to predict that. The model should learn. But the way that it learns is that it predicts logits, and then we take the difference, if you will, between the predicted and the real, and that information is used to update the weights of the transformer until after many, many iterations and many, many GPUs and many amounts of text data, it starts to learn. Do you guys see that? So this loss is a value that traditionally you always want to minimize. So that means that this value initially might be like 0.90, but you want it to go down to, let's say, 0.05 or something. That's a perfect case, so it may not get that low, but you do want it to go down. Do you guys see that? So that's essentially the idea. All right. And then so we're not done yet. This just calculates the difference. But now there's going to be a thing, I call it the three functions of PyTorch in the training. They're always there. Later on, we're going to drill down and slowly it'll make sense to you what they mean, but they're always there. All right. So there's going to be so remember, we were using this thing called optimizer, right? So we invoke optimizer, and we're going to say 0 grad. So this 0 grad is like a weird thing. Like if you had a car and you're driving it and it's all about driving the car, but eventually every time you have to brake, you have to pull a lever just to release some birds or something. It's not really related to driving the car, but it's the law. You know what I mean? So it's one of those things. This is not so crucial to understanding the whole flow, but it's necessary for PyTorch to work correctly. Do you see that? So PyTorch accumulates weights. It's got a buffer where it's accumulating values. V1, V2, V3. That's kind of its natural way of doing things. So every time you do this, you have to zero this out. So essentially blank it out so you can put in the next one instead of accumulating. Okay. So that's why that's being done. It's not so essential to the algorithm of stochastic gradient descent, but it is essential for the functioning of PyTorch to work correctly. But this is always going to be there. This is going to be followed by loss dot backward. This is the famous calculate the derivatives of the function. So this is something we have to learn later on in the semester, but that's essentially how machine learning learns. Anything that's a neural network, whether it's Iris or an LLM, there's only one mechanism. There's not 3, 5, 1,000. There's only one. And that's going to be through stochastic gradient descent, which means at a certain point of the function, you have to calculate the derivative of it. We'll talk about that later, but for now, that's what that means. We take a step, calculate the derivatives. Those derivatives give you some information, and then you make the update. And to do the update, you do optimizer dot step. So that function is the update. So at that point, all the weights in the neural network are updated by 0.003. What is 0.003? The learning rate, remember? Now, the question is, how are they updated, right? Do we add 0.003 or do we subtract 0.003 from the weights? And maybe for some of them you add, for some of them you subtract. How do you know that? How do you know which ones to add and which ones to subtract? That's the calculus part. Calculus essentially tells you if you should add or subtract. But that's done internally, and that's something that we will see a little later, okay? Gradually, we'll look at that. But mechanically, this is it. That's the whole magic that updates the weights of the model for it to learn. Any questions about this guy? This is something that every time we do a neural network, we'll do this. So definitely by the end of the semester, you'll memorize this because we do it so much and it's always the same. But just know behind the scenes, it's doing a lot. I will say this is why Torch exists. Everything else so far today, I was able to do with NumPy, no problem. The one thing that I can't do with NumPy that is pretty hard is this calculation, this training that is done by the optimizer. And that's something that only Torch or TensorFlow, and it's got to be a framework can do. Questions before we? Do you have a question? Anybody? Pardon? Yeah, so the optimizer is the thing that has the underlying algorithm of stochastic gradient descent. So it's almost like you're building. So everything that we've done so far is building a computational graph. So we take a tensor and we say that there's going to be a weight matrix and a bias. And we're going to do a matrix multiplication. We'll say mat. And then I'm going to add to the bias. And this is going to flow into a new tensor. Do you see that? And then there's going to be another weight matrix for that tensor. And what do we do with them? Another matrix multiplication. And then there's going to be another bias. And we add them. And then that flows into yet another. Let's say this is now K, right? So now I'm like introducing the terminology of K. But then this thing X over here also became Q. And then we know that these two have a matrix multiplication, right? And the result of that is yet another tensor. Right? So everything that we've been doing, it's really this computational graph in memory. Do you see that? But there are places that are fixed and places that are not. So these are learnable parameters. Do you see that? These are all learnable parameters, these blue ones. So what happens, what the optimizer does is before we created the whole architecture. During that loop, it's passing data through the whole network and changing the values, right? And producing a final result, right? Let's say it produces a final result pred, which is compared to real. What does it do with that? It calculates a difference between them. And that information then is going to be used to backpropagate to the whole network, but with the goal of modifying or updating these parameters. Do you see that? So PyTorch creates the graph, data flows forward to produce a prediction, you compare it to the real data, take the difference, And then the optimizer uses that information to update these weights and biases. Eventually, as this is complete, as this is fully trained, a next comes in, and what would you expect? This is almost this, which means you've minimized the error of the model. Do you see that? So that's essentially the whole process. And the optimizer is the thing that handles that. You create the architecture and then iteratively you're running through this computational graph, right? And then you're updating the weights of it. Okay, so that's the neural network. So if we go back now to the code, it's actually finished, right? So let's analyze what happened here. So we did a few iterations, a few thousands of iterations. And what do you see with the loss? It's decreasing, right? Okay, so it went from 4.6. Notice that it quickly jumped to 1.6, and then kind of slowly, but actually steadily, it always decreased. This doesn't always happen with neural networks. Sometimes it goes back to like 1.7 here or 2, and then transformers also have this very nice property that they always, like, I've noticed this in other things I've done, that it always smoothly goes down. So it's always learning a little bit. So essentially what we did is we just trained the model. Do you guys see that? We literally just trained. Now, is it great? Probably not, right? Because I just used one book, but the weights are no longer random. They now have values. Do you guys see that? And the goal was, remember, I was comparing the loss. Now, notice one thing that you might think is, in my slide, I had something called cross entropy that you don't see here, right? But it's because it's inside the model itself. That's just a choice. It could be outside, no problem. So what I'm going to say is, remember that it does return loss. In my example, I had something like this. I had loss, cross entropy, and then it would take what? Somebody said logits, comma, YB, right? And then we minimize it. Here, this is only returning loss because the model itself has that. So we can take a look at it. It's in here. So it's this one here. Like that. So you can see here, essentially we predict logits, right? The same thing I was saying, but instead of returning it outside, it's just computing it internally. So the YB comes in as targets, right? So now you can see you have logits and targets, and this is just like changing the dimensions. So logits goes in, targets goes into a function called cross entropy. It's going to take a while for us to discuss cross entropy. Don't even worry about that. We have to talk about entropy first and build up that. But in one lecture, we'll understand that one. But for now, understand it as quite simply taking the predicted and the real and taking the difference, and you're trying to minimize that difference. So the prediction should start to become better and better and better and better until it's as good as the real. Make sense? All right, so we're basically done. Like, this is the LLM. We'll continue to look at the LLM all semester, but but not introduce new things per se, as much as remember that part, remember this part, something like that. Because this is as far as complexity, this is as complicated as it gets in terms of the LLM. There is no, nothing more. Attention is the key. You could have maybe 12 layers instead of 6, 12 blocks, or 24 heads or something like that. Do you see that? But not really. This is it. This is the whole architecture. Okay. So, and the only thing I haven't covered is the generate function. We'll cover that in another class because that's really not necessary to understanding the training. It's only a trick, like a programming trick that we have to use of how do we grab like the last thing and pop off the next one and so on. So now what I want to do actually in the time we have left is just run this code until the end, right? So that you can see for your term project, for your homework 2, how you will use this, okay? So you should be in agreement that we've trained the model, right? So, and by looking at the losses, I would conclude that it learned something. I don't know how good it is, but the losses went down. That means some training happened. The weights are no longer random. Okay, so then the next thing is, now we are in the generate part. So you have to give it some input. These transformers work this way. You always, you give it a question, it gives you an answer, right? So even if you don't have a question, you need to give it like, hey, some input tensor of a specific shape. So that's going to be this, just giving it one sample and one value. Okay? You have to give it integer and you give it in the GPU or it's going to give you an error. So once this is called start of sentence context. So this is an example without a question. The mGenerate function, which is in the model, will take it in and generate about 500 tokens, which is about 500 letters in this case. There you go. Your first AI that speaks to you. Terrible, but it does speak to you. It's trying to say hello, right? So it's saying, "Are she got to mighty soon squared bagoo?" Although it's pretty terrible, it should actually amaze you a little bit because it's letters, not tokens. And if you look, a lot of these look like actual words, right? So it formed the word but, you, boy, I reckon. So you can see, boy, I reckon my tough boot jaws, whatever that says, that actually does sound a little bit like the adventures of Huckleberry Finn. The whole I reckon, Jaws, it's a little bit like Huckleberry Finn. What do we've got it up? It doesn't make sense, but that's only because it hasn't trained long enough. It hasn't had enough data, but it's actually already starting to pick up some patterns of language in a pretty amazing way, right? And I just trained it for a little bit. Now imagine, oh, even caught Tom Sawyer. Well, Tom Sawyer, you see? So actually this means it learned the name Tom Sawyer. I literally gave it nothing, right? So that's the example. So your GPT is trained and you can, do things with it. So we did that. Now, this is just, I think I just tried this twice. And then I have a question for it. And I'll show you that asking a question is essentially the same as just giving it a nothing token or a start a sentence token. Notice also that it's not super fast, and I'm using a GPU, so you can see that this model does require a bit of power, RAM, and things like that. There you can see it wrote a rope all boom mites. And when I put that on Rui, so it's making up words. But see, that's where tick token will help you because here it's got too much freedom to create made up words because it's letter by letter. Tick token is at the subword level. So the things that it create might sound more like actual words. Do you guys see that? So that's why Obviously, I'm not going to, that's something you have to figure out on your own as part of the project, but very important. All right, now let's look at this one. So I'm using my encoder, right? And so I give it, where is Huck? So where is Huck? That's my string. I want to show you guys that that's just some integers. You can see it's just some integers. And I just have to encode it properly. So it's got to be like for the GPU. So torch tensor, NP, long, put it on the device, which is the GPU. It's a torch tensor. Changed a little bit of the like the shape. I'm missing a T. Oh yeah, thank you. Thanks. Oops, it's even worse. Right, so now it's just the same, but in the right format. Okay, and now we should be ready to ask it the question. So remember, new context is actually where is Huck? So you just created a chatbot, right? Because a chatbot, you ask it a question and produces an answer, and that's exactly what it is doing. And simply answering questions is nothing more than just giving it a string of text. Give it some words, gonna continue doing words. So here you ask it, where is Huck? See how it even, by the nature of the model, it repeats your question back out because it's that whole shifting thing, right? But notice it says, what makes you glay? I have no idea what glay is. But again, this is a problem of having a vocabulary of just letters. Too much freedom. On a country place, see, this sounds very like Huck Finn. And then it just keeps talking. So Jim steps out with the river. So that's actually from the Adventures of Huckleberry Finn, and so on. So there you go. That's how you ask it a question. So yeah, and then that's it. There you go. We're done. So in the project, homework 2. So homework 1, you're collecting some text data. Homework 2, you'll use this exact same code, but adapt tick token into it. And you're going to train it on GPUs, which as much text data as you can for as long as you can, and for a specific task. Whatever, you're making a VED GPT. And then you're going to ask it some questions. So in the demo in class, you'll do this, like, where is Huck or whatever it is, and ask your questions. And then we'll analyze your results, see what worked, what didn't work. But that's it. So this concludes this is actually your first algorithm. Large language models is like the most complicated probably. Everything else from now on will be pretty easy. What I will do the next class, we have the exam, right? And that I'll use that. So the exam is only an hour and 20 minutes. The other hour and 20 minutes, I'll just go through this in case I miss something. Maybe that generate function I'll cover, but that's it. We're done. So in the second third of the semester, then we'll start just with regression. So we'll create, like very simple neural networks. We'll just create a whole bunch of little ones of and we'll start with a simple neural network on how to calculate Celsius given Fahrenheit, for instance. And then in the third third of the semester, we'll get into images. So that'll be CNNs, and then leading up to the stable diffusion algorithm. And that's it. All right. So yeah, so we're done. If you have any questions, read all the materials, certainly go through all the code, run it on your own. Yeah. The exam will cover pretty much until this, but we're done. Let me just close the example.